Good morning. Okay, so let's talk about M87. Okay, so what's M87? M87 is the black hole at the center of the Messier catalog galaxy M87. So, uh, and M87 is the only black hole that we have an image of, and that happened not long ago. Okay, and it was really big news. So if you hadn't heard of it, I don't know what you've been doing. But so how did they get this picture? Okay, well they didn't. It's not. They didn't take a picture with a traditional camera. When you go and you look at images of M87 on the internet, what you see is something that looks orangish and it's kind of donut shaped and it's brighter on one side than it is on the other. And I'm going to include a picture of that so we can look at it. And one of the things that um, one of the things that's important to realize is that the way that we took this picture, all right, the way that we generated this picture was not by measuring visible light. Okay, so we're still talking about waves, but we're talking about electromagnetic waves. And if you look at an electromagnetic spectrum, one of the things that you'll be able to see is that the area for visible light, okay, and usually on most pictures of an electromagnetic spectrum, they actually color those red, orange, yellow, Roy G. Biv, okay, that whole rainbow thing. And it takes up a really small, all right, if you're looking at the camera, if you're looking at this image on the screen, it's really small, but the rest of the electromagnetic spectrum is stretched out here with the visible range just taking up a tiny little bit. So the number that typically gets thrown around is that we can only see about 5% of the electromagnetic radiation that's coming towards us from space. And that's just the visible range. Okay, well, that means that 95% of the stuff that can be detected out there, we can't see it. If we just look up to the sky, we don't see it. If we use a large telescope, we're still only going to see light. We might be able to resolve that better, but we're still only going to be able to see light. So what did they do with this black hole? Because one of the things about black holes is what they call the event horizon. And essentially, what the event horizon is it's that point out from the radius of a black hole where the gravitational force is so strong that light can't escape it. Okay, so escape velocity is a big deal. All right, so if you have an object, okay, and you take that object, I take that object and I throw it up. All right, I throw it up and it comes back down. Okay, if I throw it harder and cause it to accelerate upwards faster, okay, it takes it a little longer to come down. And this is apparently hard to catch. And if I throw it even harder, it'll accelerate more and it'll initially be going up faster and it'll go farther up and it'll come back down. And that'll keep happening until at some point I'm able to accelerate this object at such a speed that it's able to escape the gravitational pull of gravity. And the stronger the gravity of the object that we're talking about, all right, so if we're talking about asteroids aren't very big. Matter of fact, the gravitational pull of your typical 10-mile asteroid uh, is so small that were you on that asteroid and you just started walking, you would have to be really careful not to accidentally launch yourself off of the asteroid. I mean, you could do it by accident. Um, so let's go to a bigger object, say the moon. Okay, on the moon, the gravitational force on the moon is 1/6 approximately of what it is on Earth. So it's a lot easier to get up to a speed that will allow you to escape the moon's gravitational pull. And then when we go to bigger objects like Earth and we obviously expend a lot of fuel in order to get things launched into space from the surface of the Earth, in order to accelerate those things fast enough that they'll actually be able to get into space and not be pulled back down. So what goes up does not necessarily come back down. It does for everyday things, but when you really start to try and come up with methods that will allow you to accelerate things fast enough, you can get off the surface of the Earth. And the more mass a planet has, then or a star, okay, or things like that, the more mass those things have, the great the faster you have to go in order to escape their gravitational pull. Um, well, when we get to things like black holes, there comes a point, and not just black holes, but let's talk about black holes. So we get to when we talk about black holes, there's a point at its radius where the gravitational force is so strong that light cannot travel fast enough in order to escape it. So escape its gravitational pull. So when we look, and that's called the event horizon. If we look at if we look towards a black hole, we don't see anything. Okay, because there's no light, and that's what we're able to see. That's what your eyes are designed for, is to see the electromagnetic spectrum within the range that we've come to call visible light. That's what you're able to see. You can't see radio waves, you can't see microwaves, you can't see gamma rays, you can't see X-rays. Okay, you can see visible light, but we can detect those things. And radio waves in particular are really nice. They're easy to detect. Okay, so infrared rays. Our Earth has an atmosphere, and one of the things that the atmosphere does is it shields us from uh, different types of electromagnetic radiation. Okay, so X-rays tend to bounce off the atmosphere and they don't make it to the surface of the Earth. Infrared rays tend to bounce off; they don't make it to the surface of the Earth. Visible light makes it to the surface of the Earth, and radio waves make it to the surface of the Earth. And what's really nice about radio waves is radio waves treat the atmosphere just the same way that visible light does. It's essentially transparent. Okay, they can pass right through those things. One thing that radio waves can do that visible light can't do is radio waves can pass through solid objects. Okay, so if you have a radio and you turn it on and you're listening to 98.6, and you go and you're carrying that radio with you outside, and you walk inside your house, the music doesn't stop. The radio doesn't stop playing. The radio signal just passes right through the walls of your house and gets to the antenna on your radio and is interpreted electronically, and you still get to listen to your music. Um, but and the fact that the atmosphere treats different frequencies that way of electromagnetic radiation is really one of the reasons that we're able to have nice warm days, because infrared radiation bounces off, okay, the atmosphere, um, but light doesn't. Other forms of electromagnetic radiation come in. They have a certain amount of energy, and when they come down in the Earth, the surface of the Earth, objects absorb that energy, and it gets turned in. It increases the average kinetic energy of those objects. The Earth being the primary one, since it's the biggest thing and easiest to hit. Okay, and if when the average kinetic energy of the molecules that are making up a an object increases, then we've already talked about this. That's temperature. It's really what we're talking about. And the temperature goes up, and that gets released into the atmosphere as infrared radiation. Well, the atmosphere isn't transparent to infrared radiation. So that infrared radiation gets trapped, and it causes and it bounces back and forth inside the atmosphere and causes things to warm up. And that's why things get warmer during the day. Okay, so so this is a good thing. But since radio waves pass through things, they pass through a lot of things. That means that those are going to be really easy to detect. Okay, we can, if we want to analyze X-rays coming from space, we have to get outside the atmosphere in order to detect those. Okay, if we want to analyze radio waves, we can just stay on the surface of the Earth and set up our satellites, and you've seen these huge drop flashlight. You've seen these huge satellite dishes that are set up specifically to collect radio waves, and that's what they use to uh, to to gather information about the black hole M87. Is they use radio waves. Okay, so we're still talking about waves, and but we're also talking about black holes. So we're getting into a little bit of theoretical physics right now. Now, so how do we make this picture that everybody looks at? Because they didn't snap a picture. They didn't snap a picture of visible light. Okay, so what did they do? Well, they essentially measured the intensity of the radio waves that were coming from this black hole. Okay, and they mapped them. They said this radio wave has an intensity of X, and it's coming from this location, and this one's from here, and this one's from here, and this one's from here, and then they represent those as color, and depending on the intensity is what color we see. So we end up seeing a nice orange donut shape for our picture of a black hole, and it's brighter on one side than it is on the other, and that has to do with the Doppler effect. Okay, so the frequency of the radio waves that are coming towards us uh, is higher because the black hole is not just sitting there; it's spinning. Okay, so and we're familiar with things spinning. Okay, you know that the Earth spins on its axis, and lots of other heavenly bodies do too. Black holes also spin. Some are thought to not do that. Some thought are to that. This one in particular is thought to do that. So when we talked about the Doppler effect in the previous video that I posted, we talked about the fact that the higher frequencies associated with Doppler effect are because things are coming towards you. All right, and the lower frequency is associated with things that are farther away from you. So what we end up seeing is a higher intensity of electromagnetic waves around the black hole, okay, around its event horizon that are coming towards us on that side. Okay, so if the black hole is spinning like this, is that easy to see? That's not really easy to see. What can I use to demonstrate that? I had a ball here earlier, but I don't know what to do. Okay, I'm going to use this since it's irregularly shaped. Okay, and it makes it easy. So if it's spinning, if a black hole is spinning like this, okay, then the bottom part of it is what's coming towards you. And when you look at an image of M87, you'll notice that the intensity of the electromagnetic waves on towards the bottom is much higher. It's brighter down here, and it's dimmer up there, and that's due to the Doppler effect. Okay. All right. So what else do we want to talk about? All right. So let's talk about how we got this image. All right. So we didn't just take when I say we, I mean we, the people of planet Earth. All right. So we didn't just take a satellite dish and stick it on the ground and pointed it at M87 and we got a picture. That's not how it works. Okay, so and there's a problem with that, and the problem is that we're looking through a small aperture, okay, at the object that we're trying to see, or the radiation that we're trying to detect. It's the difference between looking through something very tiny or looking at something bigger. And I have some activities that I want you to do, and I'm providing all the materials except for a couple that I'm hoping you have around your house. But if you don't, you should easily be able to find something to substitute with. And I base that on the idea that everybody has some kind of light source in their house. But in this case, flashlight. That's what we're going to use. Okay, so let's talk about apertures and and how we can visualize how things look differently. Okay, so you're going to need um, a couple of pencils. Okay, and I'm providing you with pencils. All right, and they'll be in a Ziploc bag at the school. Okay, and if you can't make it to the school, you're going to have to come up with your own supplies. And there's a list in the papers that I'm providing for you. I'm also going to provide a digital copy of the assignment uh, that should be attached to the same video under the assignments on Google Classroom, and you can download that and print it off. But if you want all the stuff and you don't want to have to gather it up yourself, you'll have to come up to school. And if you can't come up to school, then you'll have to just find stuff that'll work. Okay, if you can't find pencils, a couple of metal rods or a couple of sticks that are really straight, or whatever you got to use. So you're gonna need some of these, and you're gonna need a couple of these, and you're gonna need some rubber bands. All right, so why do we need rubber bands? Here's why you need the rubber bands. Okay, so I have these two pencils. All right, and these I've already rubber banded up. And at the bottom, I just wrapped the rubber band around it and made it really tight. And the two pencils are actually touching. But if you look very carefully at the top, you'll notice that there's a gap. Okay, and the idea is to make that gap equal about 2 millimeters. Do you have to measure it? No, you don't. Just guess. Okay, 2 millimeters isn't very big, but I'm also providing you with a ruler, so you can use that ruler to measure and see if you got close. And the way that this is done is that when the rubber band's wrapped around it, some of the rubber band is in between the two pencils, and that's how I got that gap. So at the top, I have a gap, about a 2 millimeter gap, and that gap gets narrower and narrower until it's gone at the bottom. Okay, and here's what you're going to do. You're going to take this, and there are questions that you have to answer on your worksheet, so make sure you read the worksheet. There's a lot of information on the papers that I'm sending you, so make sure that you go through it slowly and that you understand what it's telling you and what it's asking for. Okay, because it'd be really easy to just kind of skim it or read it really fast and then go, I don't get what's going on. Okay, so for this, and there's more than one activity. For this one, what you're going to do is you're going to take this and you're going to see how well you can resolve two light sources. Now your packet says that you're going to need tape and you're going to need a couple of LEDs and a button battery. Well, I don't have the LEDs. The button batteries are easy. The LEDs, I couldn't find any place locally that sold the types of LEDs I wanted. Right? Everything I found was too big. So I guess I have to order some of those for next year. But here's what I did at home. Okay, and I've got LEDs, but I got this. I got a flashlight to show you how you can do this. So here's a flashlight. All right, now it doesn't have to be a big flashlight like this one. I just grabbed this one because it was handy. And I think that my good flashlights are probably way too bright for this. But anyway, so notice there's some tinfoil around the end of it. So I took some tinfoil and I wrapped it around the end of the flashlight so that I covered up the lens, and I put a rubber band around it to hold it in place. Okay, and tinfoil works really good because light doesn't really pass through tinfoil. So if you cover it with paper, you'll still have some light coming through the paper because it's not entirely opaque, but aluminum foil works really well. Now, on the end of this, let's see if I can turn this so that you can see. Okay, that seems to be a good angle. If you'll notice in this, close to the center of that, I poked two holes, and I just used a toothpick. You can use anything. Just make two small holes and make them relatively close together. Okay, these are probably 3-4 millimeters apart. Okay, and when you turn this on, and see how well the video handles this. Yeah, that's not gonna work. Okay, so when you turn this on, what you're gonna have is you're gonna have 2 points of light, and you want to take this and set it up across the room somewhere. Okay, and turn it on, and go. Then you're gonna go to the other side of the room and you're gonna stand in front of it. And when you go to the other side of the room and stand in front of it, you can take your two pencils and hold them relatively close to your eye and close your other eye and look between the two slits. And I should mention, whenever you set this up, make the holes horizontal to each other so that they're side by side this way, not up and down. Make them so that they're horizontal. And you're going to take this, you're going to look through it, and you're going to see how well you can see those those 2 points of light. Okay, and I want you to kind of look and see what that looks like, because I want you to, because you'll have to give me a written description, and you're going to have to like draw a little picture of what those 2 points of light look like through the bigger end of our aperture that we created with our pencil. And then you're going to move about halfway down, and you're going to do that again, and then you're going to move down as to the point where the pencils are almost touching, and look again. All right, those 3 locations, I want you to look through your apertures, your variable aperture that you've created, and see what those look like. Now they're going to look different, and at some point it's going to be easier to tell those apart, and at other points it's going to be harder to tell those 2 points of light apart, and you need to tell me which is which. Okay, and when you describe what the light looks like, okay, a light is a light. We all know what a light looks. Okay, but sometimes when you look towards a light, all right, sometimes you see little lens flares, or sometimes you'll see a halo of light. Oh, turn the light off in the room while you do this. Okay, that makes it a whole lot easier. It's a better experiment to do in the dark. But so that kind of, if there's like a fuzzy region around the light, okay, to make sure you include that in your description or in your drawing as best you can. It's not an art class, but it is good to be able to create a visual model of something so that we can help people understand what it is we're looking at, which is what they did with the black hole when they took all of their radio intensity information and translated that into something visual that we could look at, because we're really good at seeing patterns of things that we can see. Okay, so that's basically the gist of how you're going to do the first activity. All right, so the next activity, what do we want to talk about for the next activity? The next activity, and actually that's the second one, but the first one's really simple, and I don't think you really need my help as far as the first one goes. The next thing that you're going to do, all right, so in the packet that I'm providing for you, there's instructions, okay, that go along with these pages, but you're going to have 2 pages that are labeled EHT templates, and when we in EHT, okay, so Event Horizon Telescope, okay, and one of them looks like this, okay, and then there's another one, and then there's another at the bottom of the page. So there's actually 2 on this page, and then there's a third one that's on this page, okay, and then at the back of your packet, and I believe I put those 2 at the back as well. But at the back of your packet, Mr. Witter can find it, because apparently he's not as organized as he thought he was before we started this video. What have you done? Let's see. All right. I'll find it. I'll just edit this part out of the video in a moment. Maybe I left it in the other room, so I guess I'll go find it. Oh, I didn't print it. Okay. Well, that's an issue. All right. At the back of your packet, there's a printed copy of a centimeter ruler and a compass to measure with, and a protractor to measure with, and there are 2 sine waves, and you have to cut those out. And 2 of them are for you to measure with, and then one of them is for this activity that we're going to do right here. Okay, so you're going to take this. You're going to take your first template. Okay, it's work better if I hold it straight up. Okay, you're going to take your first template, and you're going to. Do you see these 2 points right here? Okay, you're going to take those, and I have this. Okay, now you're going to get cardboard in your bag that I'm providing at the school, and you put it behind the paper. Okay, and the purpose of that is so that you can take a couple of push pins, That's what I'm calling a push pin. And you're going to put them through the paper into the cardboard at those two locations like that. I probably should have used a different color push pin than white. Okay, but you can do that. And then you're going to have two sine waves and a piece of straw. And you're gonna need some tape. All right, sorry, you need tape. And you're gonna take those straws and you're gonna cut them so that they're about the same width as the paper that your sine wave's on. Now, granted, this one is a transparency. You're getting paper, but you can still see through paper, so it shouldn't be a big deal. You can still use it. You're gonna tape this to the end, and you want to do both of them the same. All right. So the distance that your straw is from the end of your paper, okay, if it's not exactly touching it, it needs to be the same for both of them. So if you hold both of them up side by side, okay, there's two. It's right here. Okay, I have two of them. Those need to be identical as best you can. Okay. And do they have to be exact? No, because we're using papers and push pins and drawings of electromagnetic waves or representations of electromagnetic waves to do this. So it's not perfect. Okay, so next thing you're going to do, I'm showing you how to do the first one. You got to do the other two on your own. So you're going to take this and you're going to take the straw and you're going to put it over the push pin, okay, so that it stands up like that. And then you're going to take the other one and you're going to put it over the other push pin like that, okay. And you're going to take these and you'll notice at the top in the middle there's another dot. Oh, they both came off. Let me fix that. Okay, so you're going to take those and you're going to find the spot where your sine wave, you're going to make sure your sine waves are lined up. Okay, so they're not offset. Okay, you don't want them offset. You want them to be lined up on top of each other at this point at the top of your page. And then I'm going to angle the camera a little bit and see if I can get a better shot of this. Maybe that'll work. I'll look at it later. Okay, so line these guys up, all right, and make sure that your sine waves are lined up right on top of each other on top of this, and you might have to fiddle with the positioning of your thumbtacks just a little bit in order to make that happen. That's fine. Then you just make sure they stay the same. And once you've done that, I want you to start rotating them this way, and I want you to do that until the two, and when you do that, your waves are going to be unsynchronized. Okay, so you're going to keep doing that until you get two sine waves along the dotted line that's at the top of your template until they line up again. And when they line up again, you need to take your pencil and put a mark. Okay, and when you can take this off, and then take the ruler that I gave you, and let's see, where's my ruler? Here's my ruler. And you're going to go from point 0, okay, where the dotted lines intersect at the bottom between the two push pins, and you're going to draw a line from the point that you made where your sine waves line back up, okay, and you're going to draw a line. So you should have a line at an angle going from that point to 0. Tilt that up. So here's my line right here that I drew. Okay. Now all of the area, and go ahead and measure it. All right. Use the tools that I gave you to measure it. Find out what theta is, and write that down right here. And then you've got a little math work to do. All right. But all of the area that's inside this triangle that we've described here is unresolvable. Okay. All of that is unresolvable information. So we want to shade that in. Okay. And then you're going to do the next one. You're going to do the same thing on each one of these, okay? And you do the same thing on this one, on template 1, 2, and 3. And then you're going to kind of look at them and see what kind of information you can glean from comparing them to each other and letting me know what the difference is in between those two places. Now, I did not define every variable that's on here because I want you to read the information and I want you to see what's going on with that. So those are the two big activities that you need parts for that I'm providing, and and I'm providing as much as I can. So in your packet, you're going to have pencils and rubber bands and push pins and cardboard and some tinfoil for your flashlight. Um, and then you've got some stuff that you're going to have to cut out. So you're going to provide your own scissors. Um, and I think that's all I'm going to tell you. Okay, so I'm going to go back and I'm going to try to edit this video a little bit and put some pictures in so that there's some things that you can look at that will give you a better visual of some of the things I talked about. And that way you're not sitting there trying to imagine what it is I'm saying. You can actually see it in front of you. We'll see how well that works. That's going to be a thing. I'm going to go I'm going to take these papers. Now I haven't taken them to school yet. I've got to go up there and make copies and all that other good stuff and get baggies. But I'm going to go ahead and drop these off to school before I mess with editing this video. And probably, well, that's kind of redundant because by the time I post this, I'll have done all that. But anyway, stuff will be up there for you. That's all I got for now. Y'all have a good week.